Thanks for the introduction and also for the invitation. So today I'm going to talk about sort of continual learning. How do we make machine learning much more efficient in terms of incrementally learning instead of retraining everything whenever you have some changes. Okay. So traditional machine learning is basically going this way. It's like a waterfall type of thing. You have data, you learn you got a model, and then you basically go for application. But once you deploy it, the model will be fixed. Basically, it will be fixed. You can't touch the model anymore. But what happens? You have new things you want to add in, and what happens if the data distribution changes, right? So in industry, this is a solution. Your periodical retraining. So after 2 weeks or 2 months or something new you would add, you basically got to retrain your system, and which is very time consuming. Very time consuming. Obviously, energy and other human resources, everything will be very, very slow. So today I'm going to talk about mainly from this angle of learning incrementally, which we call continual learning. And incrementally means when I learn this new thing, I'm not going to use the old data anymore. I'm just going to change the models. Just change the models, all right? And how do we do? Obviously, you can do this efficiently. You can do this slowly. I'm going to talk about how do we do this very efficiently and also accurately. How do you do this pretty accurately? And sort of about the problem of sort of doesn't do, we don't want to do retraining, and the traditional machine learning also has lots of other kind of weaknesses. Okay, for example, you can't do continuously because you always do model by model, and also you have this what we call the closed word assumption. Means you assume whatever you have seen, you see in testing, you have seen it in training. So there's nothing new in the real world, which is not quite true. And of course, we can't do post-deployment machine learning. If you look at these things, and we humans are pretty good at all this, right? We never learn things in isolation. We don't say we get a bunch of data and then look at it and then we learn it, and that's it. Done. Okay, that's done. And we never do that. We always do continually and incrementally and also very, very efficiently. So I'm going to speculate later on something I'm going to say probably going to be very controversial, and we'll see whether you agree with me or not. Okay. And obviously we want the agent to do something like this as well, and very efficiently and also incrementally. Just remember these two keywords. So let me introduce the problem of continual learning, sometimes also called lifelong learning, and what are the key challenges of this particular learning paradigm. So the definition is very simple. Just say we're learning a sequence of tasks. Okay, so the sequential just basically means today I see something, I learn it. Tomorrow I see something, I learn it incrementally. Okay? I don't go back. You don't go back to do the retraining of basically use all the data to do the retraining. So what do we mean by tasks? Of course, depending on what kind of paradigm you're doing. Let's say we're doing supervised learning, that be basically a bunch of classes you have to learn. So for example, you really learned 20 classes, now you have 2 more classes you want to learn, and sort of go on and on. So incrementally, as I said, you don't use the data you have used in the past, just the new data. Okay, just the new data. So what are the general challenges? So there are 2 sort of general challenges. The first one is called catastrophic forgetting. So if you think about this problem of doing continual learning on the neural nets, so we have a sort of another thing I've not said is we have this model sort of setting. We say just like humans, you have only one brain, and then you just assume this brain is a big model, and then you keep learning inside, you modify something. You don't build multiple models. You only have one brain. So basically means you have learned all these things in the same model, the same network. Okay, not necessarily the same model, but the same network. So this is catastrophic forgetting. This is easy to understand if you think about it. Neural nets, and if let's say I really learned n tasks, and obviously the weights somehow fixed, right? But now I'm going to learn a new task. You have to change the model somehow, right? basically. Then you're going to change the parameters. Now what happens to the previously learned knowledge? You're going to destroy it. Okay? You're basically going to destroy it if you don't see the data of the previous task. So that's called catastrophic forgetting. So if you don't care about it, you just keep learning it. After a few tasks, and then your original task, that's the first task, second task, becomes completed right. There's nothing left. There's nothing left. All right. So you have to deal with this problem. So another issue is knowledge transfer. And this basically means if you have already learned something, and now you're going to learn something new, can you sort of leverage what you have in the past to learn this new thing better and faster? But not so much work is being done on this because this is really a huge problem. It's a huge problem. And this one is only applicable to a specific type of settings, which I'm going to discuss as well. So there are actually three main settings of continual learning. So the first one is called the task incremental learning. What does that mean is we are going to have lots of tasks to learn, but individual tasks are independent. They are not interfering with each other. Okay. So for example, we have this task number one. Let me get some water. So I'm talking about this thing is text classification type of problem. So the first task is to classify sentiment. For example, I'll give you a bunch of documents. You tell me each of this document is positive or negative about something or not, right? The second task could be classify relations. Right? What is this? This basic text talking about some relationship. And the third task could be say, I want to extract entities. Name the entities, for example. So you can see all these guys have nothing to do with each other. But if I give you a document, I don't tell you what I want to do, and all of them are applicable, right? You can do everything on this. So in this case, we call task-oriented. Basically means when you learn them independently. Again, we have to learn in the same neural nets. Now you cannot say I'm learning different neural networks. Okay, that's not allowed. Okay. Where again we say we only have one brain. We only have one brain. Then, in this case, when you come to the test time, you need to have the task ID. Right? Basically, I give you a bunch of documents, and task ID basically say which task you want to perform. Okay, want to perform. So in terms of definition, don't have to look at this details, but just say the function we are learning this, the X, the task, and then the Y, the Y. Okay. So in this case, we need a task ID. So if you think about this problem, obviously you also have this thing of catastrophic forgetting, right? Because when you learn in the same network, as I said, when you basically learn a new thing, you're going to modify the network somehow. But this problem has been solved, pretty much solved. Okay, pretty much solved. So there are many ways to solve this. Okay, there are many ways to solve this problem. So one of those ways is just say, I'm going to isolate the parameters. I'm going to learn here, and then the second guy here. So the same parameters. Of course, I'm saying they're sharing parameters. They are not saying they're completely separate parameters. They're sharing parameters. Okay. Essentially, you learn a subnetwork. Okay. And then you may say, okay, what is the capacity? What about the capacity? Let's say a network is this size, and can I learn a lot of stuff? Yes, you can. Okay, because there are lots of sharing. Okay, so this problem is pretty much solved. Of course, there are other solutions. For example, you can also do orthogonal projection. You learn in different directions, okay, completely orthogonal directions. Then this problem pretty much solved. Of course, in this case, problem of knowledge transfer, you can never say you solved the problem because you never know. You can keep doing knowledge transfer as much as you want, as much as you can. But this problem is pretty much solved. So the challenging problem in this guy is called the class incremental learning, which is more like every day we learn new things, of the same type, and then you have to classify them. So the difference between this setting and the previous setting is there's no task ID given to you at test time. Okay. So for example, the task number 1 is to learn to recognize pig and cat. The task number 2 is to learn the sheep. And the task number 3, chicken and dog. And task number 4 is horse and cow. And so this is pretty much emulate what we do every day. Today, for example, you have a baby, the mother today is basically pick up the picture book to say this is the pig, this is the cat. Tomorrow say, this is the sheep, and then right? So basically, when you come to test time, I just give you a picture. What is it, right? Now I'm not going to tell you, oh, you learned it in day 2. This one learned in day 3. There's no such thing. Essentially, we're building a single unified model instead of multiple models. Again, we do this completely incrementally. You don't go back to take a look at the previous task data. Right? So you think, so in terms of function you're learning, you see here we don't have a T anymore. We don't have a T. So essentially we're building a single model. So this problem is very challenging in the sense it's not just about forgetting. If you say, I'm to change the model to learn this new, the sheep, obviously have to change something. But there's another issue is if you're learning the sheep, you don't see the pig and the things you have learned in the past. But how do you establish the decision boundary? Right? Even you say, I don't care about forgetting. But you cannot establish, because you don't see the past data. You don't see the past data at all. However, there is a solution to solve this problem. Okay, there's a solution to solve this problem. We'll see. So this is called the inter-task class separation. For different tasks, the classes, they cannot be separated because you don't see the data. You don't see the data. And so this problem is so difficult, and there's no application in the real world of continual learning because the accuracy cannot beat retraining. Okay, I basically put all the data together, I train the new model. So that we also call this joint training. This basically means to pull all the data together at the joint training. So in real life, in practical application, if the accuracy is not good, then you're not useful. Okay, useful. But now, this community is getting there. It's getting to achieve the retraining accuracy now, pretty much. Okay, achieving that level of accuracy. So then obviously the thing is, if you have that problem and also forgetting, so what is the way to solve this problem? Okay, what is the way to solve? What is the correct way of solving this problem? Okay, correct way to solve this. And there's another setting which is called domain incremental learning. So this one, the first one was called the task. The second one is class incremental learning. There's a domain incremental learning. So domain incremental learning is much simpler. Just say, I'm learning exactly the same classes, but they come from different domains. For example, if you think about the, let's say, sentiment classification, you classify the document into positive and negative. But in one domain, you might be training on the car reviews. So next domain, you may be training on cell phone reviews. And the other one is beer reviews. So can you do this? Can you do this incrementally? And that problem is much easier, and not many people works on that particular problem. So I'll talk a little bit about theory and how do you solve this problem. Okay, how do you solve this problem? And if you think about this problem as the original definition, and then essentially it's the probability. So this is basically say the X belongs to a particular task, a particular class in this task. What is the probability of that? Okay, it's a probability. Is a multiplication. Let me do this. So it's the product of this guy belongs to a particular task, right? And then given that task, what is the probability of X belongs to that particular class? Belongs to that particular class. Okay. So this is called within task prediction. So basically, this is a task ID prediction, right? We're not using Y, we're using the domain, okay, using the domain X. Okay. Because Y is not, semantically, Y is not well defined. Okay, so not well defined because we need the domain to be obviously we have to make some assumptions. So the domain has to be sort of independent. Not intersecting. Okay. And so the theoretical result, so this is the called task ID prediction, is the within task prediction. Okay, within task prediction. So the theoretical result basically says, obviously this guy and this guy are necessary, right? Sorry, not sufficient. If you make this guy high or this guy high, and obviously the CIL will be high, right? The sufficient condition, right? Okay. But we can also prove these are necessary conditions. Necessary conditions. Okay. And so the major thing is actually this part. A task ID prediction is basically correlated with out of distribution detection. Okay. So why this is the case? If you think about, just now I explained this particular thing called inter-task class separation. Okay, inter-class separation. It just means when I learn let's say when I'm learning the sheep, I don't see pig and cat at all. That means there's no way I can establish the decision surface, right, between these three classes. But there is a way, right? What is the way to separate them without seeing, when you learn sheep, without seeing pig and cat, I still can separate pig and cat. And I still can sheep, pig and cat out of distribution detection, right? So you learn yourself, you also know everything which is not you. Correct?
This is similarity, right?
Sorry?
That's the same as computing the similarity. I get the query, how similar it is to the pixel that's synced, right?
Yeah, you can say that. Basically, that's out of distribution detection, right? Okay. So I'm not going to talk about this theorems or other things. And obviously, what I'm saying is this out of distribution is bounded by a number of tasks. Okay, it's bounded by a number of tasks. Obviously, you can say, take the limit in this number of tasks, then it becomes unbounded. Okay, unbounded. And then later on, we're going to talk about out of open world continual learning. And this theorem is not, sort of need to be extended. Essentially need to be extended, but essentially it's pretty much the same. Then this is the result. You can see this is the previous baseline, and this is pretty much the best here. And this, if you just use this way of solving the problem, you increase the accuracy quite a lot. Okay. So how do we solve this problem? We still have that forgetting problem, right? We have saying, yeah, you can do out of distribution detection, but who is going to deal with that forgetting problem, right? Who's going to deal with it? And it turns out when we set a TIL, that's already dealt with the forgetting problem. Okay? And then we just say, one of those TIL algorithm, either this one, there's no forgetting. Okay? And then for each individual model, for each task in the model, instead of building a traditional classification model, we're building an OOD detection model. Okay? So this CSI is one of those pretty good out of distribution detection model. Okay? So essentially, we say HAT plus this and this plus CSI. So this essentially is say, I'm going to use those algorithms are sort of parameter isolation algorithms. Learn a subnetwork. Okay, subnetwork. And so you can see this improves quite a lot. Okay. So how do we achieve optimum accuracy efficiently? Okay. Obviously, people have done a lot of work in the process. And here I talk, what do we mean by optimal? So optimal means joint training, just like traditional retraining. Okay, you basically put all the data together, and the paths and the current, everything together. You do a traditional supervised training. Okay, so we're training all fine-tuning your language models. Okay, so can we achieve that kind of accuracy and very efficiently? And why can we do efficiently? Because it's incremental. Okay, incremental. And also we're going to solve this problem in an analytical sense, which means that's a closed form solutions. You don't really need training. You don't need sort of a gradient-based kind of training. So in this case, we need language models. Okay, language models or image kind of pre-trained models. And then the interesting part is we treat these language models or foundation models simply as a feature extractor. We're going to freeze everything. I just need the encoder of this guy. Okay, give me the feature. Okay, the encoder give me the feature. I'm going to pick up the feature and just directly go to do classification. Okay, so in this case, we are using linear discriminant analysis, not exact linear, but incremental linear discriminant analysis. So this guy has a closed form solution. You don't really need to do any training or all this kind of stuff. So what do you need for linear discriminant analysis? You need a mean for each class, right? Because you have the data, you compute a mean, which is incrementally, that's no problem. And the assumption says every class, all the class have a single shared covariance. You don't build covariance for each individual class. You can, but if you do that, the memory is going to be huge, right? Because it's going to be a square matrix, right? Each class will be a big square matrix. And for this guy, we only have one, which basically means this memory is constant, right? It's that amount, fixed. As task goes, still the same memory. Okay, you can learn any number of tasks, same amount of memory. Okay, and this does surprisingly well. We're using, of course, we have something else. We just say you use the kernels to expand the features. Let's say you got about 300 something features from this language model. I'm going to expand it to 5,000 or something like that using the kernel function. We're using an RBF kernel, and we don't use the matrix. We don't use the kernel matrix. It just basically produce me approximate individual feature for me. That's all. Okay. This is the random Fourier features. For each feature you give me output, this guy is going to automatically expand it to 5,000, 10,000. We use 5,000. Okay, pretty much. That's pretty much good enough. 5,000. If you see this result, you'll see this is the optimal upper bound. Joint fine-tuning. Fine-tune the model. Okay. You see the accuracy are here on the sense. There's no natural language task. There's no individual natural language task. You can see this KLDA, it's pretty much doing as good as your fine-tuning. As good as your fine-tuning. There's no forgetting. Right, because I'm not modifying any parameters. Okay, but you can say since we're computing those covariance incrementally, does that cause any forgetting? If you try experiment, no, it doesn't. Okay, the result does not change. You learn more and more, but the accuracy for individual tasks doesn't change. Okay, so basically means that incremental covariance computation is pretty accurate. Okay, pretty good. Yeah.
This seems to do better than joint training, like at least in 3 cases. So is it just
I think it can be a little bit. If you want to compare, this one is probably the best to be compared because this one has a little bit of a ensemble kind of thing. Because you remember just now we say we are random features, right? We're going to expand it random way. Now you can random expand to 5, right? And then you can do a voting at the end. So that gives you a little bit of lag. But you can just compare this one. This is just one. It's really good enough, right? Pretty good. So this is the natural language. And this is used the BART-based model. And then these are the traditional sort of continual learning models. You can see this is a nearest class mean. We don't use covariance, just use the mean. It's really doing pretty well, right? It's much better than the previous task. So you can also do LDA without expanding the feature space with the kernels you also can improve quite a bit, And so this is for the BART base. Obviously, I mean, language model has so many of them, right? Has language model, so many of them, and we tried, all those things. And this is the sort of bigger one, Mistra 7B and this T5 3B. And so you pretty much match the result. Can match the upper bound result. For the images, we are not able to achieve that upper bound yet for some data set. So the reason is, part of the reason I believe is the image models, the pre-trained model are not as good as language models yet. Okay, image model. So you can see here, this is the KLDA, and this is the joint upper bound. So this one is okay. This one, you see, got a 1% loss. This got about 2-3% loss. And this one is also fine. For this, another one, Dino, this is a very strong model. This is a very strong sort of model. They're both not as good for these two data sets, not as good as the baseline yet. Okay, not baseline yet. And sorry, not as good as the joint upper bound yet.
Question.
But this should be achievable. Yes.
Yeah. So I think Dino is not diffusion-based model, right?
No, it's not. No, it's still yeah.
It's kind of thing. And do you think the diffusion-based model can achieve better result?
I don't know.
Okay.
This thing you have to try it.
Sure.
Yeah, it's very hard to know what it's going to be. But the language model is pretty good. The language model is pretty good. And I say this, we're saying we want to do accurate, we also want to do efficient, so continual learning. We just show you it's accurate. Obviously, this is very efficient too, right? Because there's a closed form solution, it's not true. Right? You only need to keep updating your covariance. Okay, covariance. The mean is there's no computation involved. Right? So this is just the majority of the time is actually in when you go to the language model, right? To get the feature, that takes more time than you do the final computation. A lot more time. I think it's about a few minutes. This is only about a few seconds. Final to compute. So this is very, very efficient. And so if we can do this way, keep doing this thing in terms of a very, very efficient way and online, incrementally doing it, you don't really need a lot of computation. Okay, you don't need a lot of computation. So now I'm going to make some kind of controversial observations or statements. Let's see what they agree. Okay. So you can see when you have you have a very good foundation model, language model, your learning is so simple, right? You just a distribution. You compute some statistics, the mean and the covariance. Those are very, very simple to compute. Okay. So if I give you these three type of fruits. If you imagine a baby start to learn to recognize these things, the mother shows a picture book that this is the apple, this is the banana, this sort of grapes. Does the baby actually learn to start to figure out the features and know what's the difference to compare everything? Or the baby already know they are different. The baby is only learning the name of this object. So my basically conjecture is the baby knows they're different. The baby is only learning the name of this object. They are not learning a classifier. So the human learning is very simple. It's not like machine learning. Very, very simple. So that's why we are learning so fast, so quickly. Means the humans don't learn features. The feature is building in your brain. Yes?
I guess as you say, it's controversial. If like the twins, right? You look at them, you do compare them to see who's who, right? So if they are the objects are very distinct, like apple and bananas, you're right. But if they are similar,
Those are very fine-grained things. Yes, I agree. Yes, but again, you can figure out what the difference is, right? You don't really see. I have learned some new features. You have not focused on those things. You don't really think, oh, this is a new feature I've never seen it before. I said, oh, this is the triangle. I've never. Oh, what's this? Never seen it. You don't do that. You know that. It's just you have not focused on those fine-grained things.
This is only for classification you're talking about, right?
I'm not sure.
Okay.
Yeah, I'm not sure because we're only doing classification. So I believe that why the humans learn so quickly because the features are really in your brain. So you only need to do something very simple to recognize they are different. Kind of different. So the knowledge of each object allow the baby to recognize each object, and also this is out of distribution detection. So if you give the baby an apple, and then you say the banana is this apple, the baby definitely will say no, this is different. You don't need to. The baby doesn't need to learn out of distribution model. So that basically means for everything people have is a distribution by itself. It has nothing to do with other things. You are you, nothing to do. There's no such thing of comparing and see what's the difference of the things in terms of the representation level. I'm not sure this is true. I believe this is probably true. It probably is true. And so the implications to human learning representations? Probably not. Okay. Yes.
Is this, I mean, maybe it's completely unrelated, so feel free to just ignore the question, but is this kind of related to like how this Chomsky's theory of linguistics is that we have an internal grammar, so it is like...
Yeah, it's related to universal grammar. Mm-hmm. Yeah. I agree with the universal grammar. The things are really in the brain. It's not you learn those things. Anyway, should we continue learning? Obviously no, and then, so the AI's most important task is still training good foundation models. Everything else is just secondary. Even, Natasha just asked whether this is just for classification or what about reinforcement learning, what about clustering, all those things. I believe they're probably the same. It's just we haven't got that model yet. Language model is the one which is simplest to learn. And the image are pretty good now already. Okay, pretty good already. And so anyway, I hope this is okay. And some people may not agree, but some. And also there are some neuroscience justifications. Neuroscience essentially says. We have a stable representation in the brain. Stable representation. They call the term stable representation. But this is pretty much intuitive too, right? If you don't have a stable representation, those people who are doing this, they have those things, and they have those EGC things, ECG or ECG things in your brain, and they want to predict what you're thinking about, right? So they learn the patterns, right? If you don't have a fixed pattern, there's nothing you can learn, right? Okay. And you can see some nature, there are some papers which talk about this kind of thing. The representation is pretty much stable. Pretty much stable. Then we can also talk about, do I still have time?
You have till 3:30.
Oh, it's 3:30. Okay, good. So just now we're talking about the problem of continual learning is the system is given the task and given the data. So can we make this whole process completely autonomous? Means the system detect the task and collect the training data by itself. So just like with humans, we just go out and we learn ourselves. We don't really have to get the teacher always follow us to go with it. Okay? So this is called open world continual learning. open world continual learning. So the first task is, let's assume you're a self-driving car, and then you go out, and you drive around. Then the first thing you see, you basically classify all the objects you encounter, right? But you also you want to detect, oh, this is something I've never seen before. Can you do that? That's the OD detection, right? Okay. So if you don't see anything novel, you're not going to learn, right? As a human, you don't see anything novel. You basically just apply your knowledge. You're not going to learn anything. So this is the motivation. That's one of the motivation people learn new things because they see something they're not familiar with. And so the detection. And then the second task is incrementally to learn these new objects. Okay, learn to recognize these objects. After they are learned, they are labeled. So who can label this? Nobody, right? Humans, right? Who else can label these things? Of course, in the computer, you can learn this. You can label this number one, number two. You don't label this actual name for this thing. If you want to get a name for this object, you still have to get from people. Okay, get from people. So, which is the same as we humans do, right? When we see something, oh, what's this, right? You're gonna ask somebody, what's this thing? And the guy tell you, yeah, this is a pig. Then, this is the pig. Then you learn pig, right? You don't really need anything else. You don't need anything else. And so in this model, we call it CLM plus, and the theorems, the previous theorem still applies, but needs some extension because in this case, the out of distributed detection is no bound, pretty much no bound. Previously, we have a bound in terms of the task you're doing. So this is essentially learning on the job or learning post deployment. So after the model has been deployed, you keep learning. You keep learning. All right. And I will not have time to give you an example of actual system we have, but this is just give you an example to illustrate. For example, this is the greeting robots. Have let's say roaming around in the hotel lobby and have some small chat with the guests, right? For example, when this guy saw this guest, John, and he knows this guy before. Hello, John, how are you today? Right? And then can start some chat. But what happens if the guest is new? And this is the out of distribution detection. Then to say, okay, recognize the guy is new, and then you have to react. So there's a lot of story behind this. And so when you recognize the new, you have to react. Okay. In a self-driving car, this reaction is very, very complicated. In this case, it's just very simple because let's say you see something in front. What are you going to do? You're going to stop, or you're going to go slowly, or you're going to go around. Right? So there's lots of decisions need to be made. It has to be made. And I'm just making this very, very simple. In this case, of course, it's simple. Just say ask. Just ask. Even in natural language, this could be very different. Could be very complicated. For example, I say, switch off the lights in the kitchen. I don't understand. You don't understand. Which part you don't understand? Okay? Because you have to react. You have to ask me questions. If you say, I don't understand, then what do I answer you? Okay, what do I answer you? So there's a lot of things behind this. Okay, lots of things behind this. And I have a longer talk, which is very complicated, what's behind this. So let's say, I come back to this one and just say, the guest say, oh, my name is David. Okay, David. Then let's basically get a class label, right? Get class label. And then obviously learn to recognize David is pretty simple, right? You take some picture of this guy, and that's it. That's it. And then incrementally learn to recognize this person, which is also very simple. Okay, for the face recognition of the things, now it's pretty much done. So next time when you see David again, you say, hello David, how are you today? Right? And so you can see in this process, there's no engineer involved. Just the bots go off and do everything himself. Okay. And we also have some natural language type of thing. And previously we just recognized that's still an application in the sort of image kind of thing. But you can also do in terms of natural language. And I don't think I'm going to explain this a lot. It essentially says, this is just like Siri or the Alexa, and it's a natural language interface. You ask this guy, this sort of system to do something for you. The system basically gives you some answer. You say, for example, what's the weather today? Then Alexa comes back, whatever the heck weather it is. And what happens if Alexa does not understand my intent? Okay, what are you going to do? So this is basically OD, right? All the distribution, it does not understand. Okay. So then obviously you got to ask. You got to ask. I mean, then when you ask, what do you ask, right? Okay. So for example, in this case, let's say, turn off the lights in the kitchen. And this is novelty detection. Basically, this particular system does not know what does this mean. Okay. And then this is the second step, is the novelty characterization. So this is a very complicated task. So this project was done with hundreds, I think more than 100 people. This is a DARPA project. It's more than 100 people. And when people comes to this, people only can do detection. When they come to characterization, nobody knows what to do. Why? In this case, it's easy because if you just say, turn off the light in the kitchen, and then you say you don't understand. You don't understand. But then obviously you have to react, right? So what do you react? So you have to characterize what is the thing you do not know. You ask about that thing. Right? So in this case, maybe you say, oh, light in the kitchen, everything is okay, just I don't know what's to turn off. Right? Then you can ask, oh, sorry, I didn't get you, and do you mean switch off the light in the kitchen or switch on the light in the kitchen? Instead of asking some other nonsense stuff, right? In a self-driven car, this gets very difficult. Why? Because when you see in front of the thing, there's a thing in front, and what are you going to do? So you have to characterize, for example, that's a moving object. Then you have to say, oh, this guy is moving in this direction, or in this direction, or this direction. If in this direction, I can slow down and wait for this guy to cross the road, right? If the guy is moving towards you, then you probably have to stop or something like that, right? If the thing is not moving, it's just stay there, you probably have to go around or something like that. So when people come to this characterization, forget about it. Nobody knows what to do about this. Because you need lots of common sense knowledge and lots of background knowledge. Anyway, in this case, it's much simpler. Just say, yeah, you sort of know which part, you probably don't get it. And then you ask that part. And then you say, turn off, the user will answer you, oh yeah, I mean this one, option number 1. Then you know, turn off the lights is the same as switch off the lights. Okay. And then you can learn this fairly easy, incrementally. So next time, you will have no problem. People talk about this thing. And somebody actually implemented this system. And this works fine. However, they see some other problems. So they implemented this system for taxi drivers. They test this with about quite a large number of taxi drivers. And in the end, they can't use this thing because in the practice, you have even more problems. So what are the major problems? The major problem is that many guys, most of the people, they're not so disciplined. For example, I say, play this song for me. So I don't understand. I ask you, do you mean this? The guy, oh, I want to go to Chicago. Forget about it. I don't care about your previous question anymore. Oh, then the system cannot do anything. And then also situation is, now I'm going to talk to the guy sitting next to me. I don't really answer your query. So this gets, you see this thing gets really, really complicated when you want to make this learning completely autonomous. It's very tough. But it's a very interesting direction. And we did some work on how do you incrementally train your language models. Instead of when you have bunch of new data or something, you're going to retrain your whole thing, and that's not going to be sustainable. So how do you incrementally to train your language model? that's pretty much what I want to say. So in traditional training and retraining paradigms in practice, people always use that, and they're very efficient and also very much resource consuming. And when we do this continual learning, all these things, we can cut down all those things drastically. Okay, drastically. In the past, it was just because the accuracy was not good, very hard to use. But slowly, the community is getting there. It's getting sort of the same accuracy as you do the retraining. Okay? If that's the case, then we pretty much can use the same in practice. However, for the open world, as I told you, characterization is so tough. You cannot ask, you say this in front of them, you cannot just ask everything, right? Ask people. You have to know something to make a decision. You also have to assess the risk. For example, the guy in front of you is a piece of leaf. Let me just jump to it, right? Right? You can just suddenly just stop. This is what happens in real life. This self-driving car, just stop. Okay, just stop. And so hopefully in the future we can achieve this, which is basically what they, I don't know which company was saying, learning from experience, right? This is learning from experience, from your own experience. Okay. And that's it. Thank you very much. Any questions? Yeah.
How do you frame reasoning into like your framework of like continual learning? Is it like, do you see it as, for example, sequences of OOD, like, or is it something different? Like how do you even define reasoning here?
A sequence of OD?
Yeah. So for example, I could say, let's say I see an object, I've never seen this. I say, okay, this is similar to this, and then from that, this should be similar to that. So probably it's like this.
So yeah, the similarity here is not explicit. It's more implicit. So in terms of OD detection, what is the similarity you use? So in this case, we're using Hanabi's distance. And I think human beings are really able to do that. You know what this and what that is not this.
But that's
Unless
very
they're-
constrained
unless
to
they're
visual.
very
I
simple.
feel like that's something with the visual brain. Like
Yes.
that's not
Yes.
reasoning, for example.
yeah,
Like we
yeah.
don't naturally know math. I don't know.
No,
right?
no, we are not naturally
Yeah.
no maths, but yeah, the visual perception, one talking
Yeah.
about perception, and also the language.
Yeah.
Yeah. So the human, I mean, I sort of definitely agree with Chomsky about this. Now we do have a universal grammar in your mind. If you don't, you cannot learn, right? For example, even the perception, there's something you can't see. How do you learn it? You can't learn it. Everything you can see is really there. It's really inside.
Thank you very
No
much.
questions? All right, good.